Welcome back, everyone. In this video, we're going to be diving deeper into some of the interpretations of what a derivative is. And we've talked about what a derivative is in the past. It's the slope of the curve at a point, it's the slope of the tangent line to the function at a point, or it's the instantaneous rate of change of the function at a point. And so far in this course, we've primarily focused on the first two interpretations, and in this video, we're going to be going further with instantaneous rate of change, which is how we usually talk about the derivative in applications. So I'm going to run through a few different situations and go over how we can talk about the derivative in those different situations. Let's say that we had a function that tracked how far a car was away from home in miles after some number of hours. And let's call this function s of t. And before we even talk about its derivative, let's make sure that we know what the units of this function are. So what am I plugging into this function and what am I getting out? Well, I'm plugging in t, and t represents how many hours have passed since this car left home. And when I plug in t, I get out miles, and so I know after some number of hours how far this car is away from home. So if those are the units of the position function, what would the units of its derivative be? That being s prime of t. Well, that t is still the same t as before, so the input units are still hours, but what is the output giving me? Well, it's no longer miles because the derivative is a rate of change. It tells me how much is the output changing as the input changes. And in the context of this problem, that would mean as 1 hour passes, how many miles has this car moved? And even more simply put, that would be miles per hour, which I know we've all heard before, and that makes sense because that is a rate of change. It's not an amount, it's a rate. And I think this example is familiar enough to not be too complicated, but let's look at some more exotic applications that certainly would not be as familiar. Let's say that there's a manufacturer that produces bolts of a fabric with some fixed width. And perhaps they have a function that can tell them the cost of producing some number of yards of that fabric, and we'll call that f of x. And once again, before we look at the derivative, let's make sure that we know the units of this original function. And I'm plugging in yards, and I'm getting out dollars, which makes sense because I want to know how much a certain number of yards is going to cost. But what about the derivative of this function, that being f prime of x? And once again, much like the last example, the input is not changed. We're still inputting a number of yards. We're getting out the increase in production cost after producing that number of yards. So the input is yards and the output is dollars per yard. And using words, the function f prime of x is the rate of change of the production cost with respect to the number of yards produced. Economists would call this the marginal cost, but that's not a word you need to know for this class because this is a math class, not an economics class. So that followed roughly the same as the first example, but what if I want to get more specific? And let's move part A up to the top so I can make room to ask another question, which is, what would it mean if I said that f prime of 1,000 was equal to 9? Now we've already talked about the units, and so we know that 1,000 is 1,000 yards. So this is after 1,000 yards of fabric have been produced, and the output, the 9, is dollars per yard. So after 1,000 yards of fabric have been produced, the production cost is increasing at a rate of $9 per yard. So this would be important to know if you were a manufacturer, because after you've produced a certain number of a product, you'd want to know how much would it cost to continue to produce this product. Because maybe after you've got the manufacturing process down, it gets cheaper over time, or maybe it starts to get more expensive. I don't know, I'm not a manufacturer, but these are all things that you'd want to take into account if you were running a business. For the last example, let's look at the US national debt. And let's say that we have a function that tells us the US national debt in billions of dollars in some given year. And to save some space, I didn't write out the input and output units, but the input unit would be the year, and the output unit would be billions of dollars. And notice that the output is not dollars, it's billions of dollars. And so if the output was 1, that would not be $1, that would be $1 billion. Let's say that from the year 1990 to 2000, the function increased from 3,000 to 5,000. Let's see if we could give an estimate for what d prime of 1990 would be, and if we can interpret that result. Now we can't actually figure out exactly what the derivative at 1990 would be because we don't know what the function is. We don't even have a graph of the function, so we can't find it exactly. But recall that the average rate of change can give a good estimate for the instantaneous rate of change. I mean, that's how we first came up with the derivative. We started with an average rate of change and we refined that estimate further and further, and we let that limit go to 0, and then we got instantaneous rate of change. And so while I can't determine the exact instantaneous rate of change, I can certainly find the average rate of change from 1990 to 2000. And as we've done before, that is the difference in the outputs, which is 5,000 minus 3,000, divided by the difference in the inputs, which is 2,000 minus 1990. And we simplify that, that is 2,000 divided by 10, and that is 200. And for these kinds of problems, you should definitely put the units at the end. So this would be $200 billion per year. And the way to interpret that using our words is that in 1990, the national debt would have been increasing by roughly $200 billion per year. And again, that's an estimate because we used the average rate of change from 1990 to 2000 to make this prediction, but it should be a decent estimate. So I hope that these few examples gave you an idea of how to interpret what a derivative is in context. Now there are infinitely many different applications and contexts in which you can talk about derivatives, but they all follow this same sort of idea.